So let me remind you one more time what did we get as the key formula. Basically, these two equations I highlighted now are the key formulas. They are first order time-dependent perturbation result. The physical meaning and then how to apply them are more important than deriving it. I already derived it for you in this appendix. So the first equation answers the following question. I pretend the atom only has two levels called 1 and 2, but that 2 could be any other level other than 1. So therefore, if you have many levels, you just add up the results. Okay, we will do that today. So equation A9 refers to the following question. If the system was certainly in level 1, so A1 is 0, that is the initial condition. A2 is the probability amplitude of finding the system to be in this state called number 2. At a time t, after the perturbation, the time-dependent perturbation has been turned on. So that is equation 9. Equation 9 actually gives you the rate of growth of A2. So that is a differential equation for A2. And then if we formally integrate, that is to say, solve this differential equation for A2t, it's just an integration formula. So we have to integrate over t, we throw the dt to the other side, integrate over t, then we get the most useful result, that is the equation A10. So let's look at the A10. The key idea is that there are two integrals. One has to do with space, and it has a structure, a rather familiar structure now. The initial state, it is in an eigenstate of the atom, phi1. The final state, we are asking that what is the probability amplitude that it is found in another eigenstate called 2. So phi2 with a complex conjugate, and then phi1, and in between the perturbation. Now that is rather natural. Even that the same structure appears in time-independent perturbation theory. We need this perturbation to take the system out of the initial state 1. If we don't have this term, only the atom 1, this integral will be 0. So we really need the perturbation to take the initial state out to some other state, and then the probability is found by projecting whatever the state may be onto our target state, state number 2. Therefore, we have a spatial integral that is a matrix element in general. So you have h prime 2, 1, okay? But we are dealing with time-dependent perturbation. Therefore, when we ask what is the consequence at t, we have to allow the inference to act from time 0 when it was turned on to time t. And we have the time evolution factor due to the H0, due to the atomic Hamiltonian. Okay, so we have two integrals. One has to do with space, another has to do with time. That's the structure of the answer. In particular, in our context, earlier we introduced the form in the electric dipole mechanism for atom interacting with light. It is the electric dipole moment represented by minus the charge, minus E is the electron charge, is position vector. So this is the matter part, dot into the field. Okay, so the structure is minus electric dipole moment dot into the external field. In doing this, just to remind you, there's one small approximation behind it. The wavelength of the EM wave is much longer than the size of the atom. That is usually the case. The wavelength can be hundreds of nanometer, where the atom is angstrom in size. So it is perfectly suited for our general formula. We have a spatial part in the interaction. We have a time varying part in the field. We have two integrals. So the spatial one that has to do with the electron in the atom will enter into the spatial integral. So this is initial state of atom, final state of atom. It has to do with one thing in the middle. That is the electric dipole moment. More specifically, the charge can be taken out. It has to do with a R, the position matrix element. The time part cosine omega t goes into the time integral. We are asking the answer at time t, therefore we cannot use the t again for the integration symbol. So this is a dummy symbol to be integrated over. So that is omega t prime, dt prime, everything becomes t prime. We in it over to the time that we want the answer. And immediately as promised, we see this double integral factorized into a spatial times a temporal integral. So we have a spatial integral, has to do with the atomic state, initial final with the R in between. Then we have a time integral that has to do with the eigenvalue of the atom and the omega t of the field. So here we will see some energy criteria coming out. H bar omega must be E2 minus E1. You will see another possibility. That is to say, there is a criteria coming from this integral about H bar omega of the light related to the energy difference of the two states that we are considering. Okay, so all the physics will follow from this final line. Okay, so today our plan is to take up this equation, look at the consequences. For example, if this is 0, then you have no chance of seeing the atom to be in state 2 after time t. That is a forbidden transition, not allowed. Okay, therefore we will see selection rules. As advertised, the temporal integral will give us a criteria between H bar omega of the light and the energy difference of the two states that we are considering. Everything, the results are common sense. I'm trying to convince you that Schrödinger quantum mechanics provide us with all the justifications of the so-called common sense. Okay, so that is the idea of the lecture today. So let's start the first thing, collect key results from that final equation. So I copy the same equation again here, okay? And I already explained the anticipated consequences. Spatial integral will give us selection rules. What is allowed, what is not allowed. And this will give us an energy criteria, okay? Then let's proceed. First, with the temporal integral, the integration over time. You will see some elementary integrals. Don't be afraid, just work it out. You know every step, okay? There may be 1 or 2 steps that I skipped, but that can be easily filled out, okay? So now, first step, record. In your high school, you have this cosine theta equals EI theta plus E minus I theta divided by 2, all right? So that is our starting point. Immediately, you see physics is fascinating. We have a real field coming in to interact with the atom. Immediately, you see two possibilities. We have a minus omega in one term. We have a plus omega in another term. We need both of them because we will have stimulated absorption and stimulated emission. You will see that each of these terms is responsible for one process. How wonderful, okay? Common sense, mathematics, physics form a triangle that help us understand nature, and that is the essence of physics. So let's be very concrete. For example, from now on, the spatial part, we just write it in a shorthand notation. In particular, let's make the case simpler by considering linear polarized light in the Z direction. So the E field becomes polarized in the Z direction with an amplitude and a time oscillating behavior. The perturbation, therefore, the dot product will take up the Z coordinate of the electron in the atom. So I have the nucleus, the electron has some coordinate. If it is Z linearly polarized, I only pick up the Z coordinate of the electron. The dot product comes out, you dot Z, so you pick up R dot the unit vector Z, you pick up the Z, right? So the spatial integral becomes the Z component of the electric dipole moment. In general, there's a position vector out here. For simplicity, in this example, I will simply use Z. Thereby, the spatial integral can be written in a shorthand. Initial state on the right, final state on the left, with Z in the middle. So that's what I meant. And then, or more generally, this combination is the Z component of the electric dipole moment. Thereby, it is the matrix element Fi of the Z component of the electric dipole moment. Okay? Now, more generally, it should be a vector and dot into the field when we consider general polarizations. Let's do that. Then the first term can be written in a very compact form. It is just Z Fi, okay? So from now on, for the moment, we will use this shorthand notation for the spatial integral. We will pick up a E here. So I have a E. There's a field out there. So there's a field strength. Put it there, okay? So from now on, we will focus on this time part. This comes from cosine omega t can be written as EI omega t prime minus I omega t prime, okay? So let me take you through, okay? Do you see why we have two terms in equation 15? Because this is really important. You understand? The field that goes in interacting is real, and therefore we have two terms, okay? Now, let me advertise. For those who can see or sense the mathematics through, immediate, you see, you have some fluctuating thing up in the face, okay? If this is something Then sometimes it is positive, sometimes it's negative. Over a reasonable duration of time, everything cancels out, you don't have anything. Now, that is the feeling, okay? Now, if you don't like that, fine. This is the simplest integral to do, okay? Exponential integral, you cannot d it away, you cannot in it away, so you use chain rule, you can do it. But I'm just conveying the sense. But there is one case that this will integrate to something. What if this thing is 0? Okay? If this thing is 0 or close to 0, then you will have a 1 in the integrand. Of course, this integral will be t. All right? So immediately you get a sense. If that thing up in the exponential, okay, the bracket turns out to be 0. That is to say, the initial state minus the final state energy is positive, light omega. You do not have negative frequency light, okay? This is a mathematical thing only when you do Fourier transform, okay? But in reality, omega of incident light is positive. So the right-hand side is positive, but you require initial minus final is positive, okay? Therefore, that will refer to a case where the final state is lower than the initial state. Therefore, the first term is stimulated emission. Remember, our initial condition is 1 is occupied and 2 is some other state. The first integral indicates the condition that we expect there is a final state below the initial state, and if h bar omega is correct, there will be emission, okay? Because the integral will not be 0, you have some finite probability of finding it in the final state. Now, the second term, again, same argument. If this is close to 0, you will get something, okay? Then you will see that it is final minus initial being h bar omega. Now, that is more ordinary, right? Your common sense. Initial is here, h bar omega comes in. If h bar omega is right, right means the difference between final and initial, there will be absorption by the electron and go up. So that will be absorption, okay? So summary on this point, the two integrals refers to two processes. We introduced the 3 processes, right? There is a spontaneous emission that is troublesome. Now we use light, incident light, to stimulate the atom. Immediately we see in one theory, one formula, we will see 2 processes coming out. Okay, that is very nice in terms of a physical theory. So this is the sense. If you don't believe it, then let's work it out. Here, I carried out the integration in one step. I encourage you to try that, but it is easy to see. So exponential, you just change the variable, therefore you can do ex dx, okay? So you can do it, and then you evaluate it at 0 and t, the lower and upper limit. For the first integral, actually, you get this. Then after you do the first one, you don't need to do the second one again. You just see the minus sign where it goes in. It gets that, okay? As advertised, this will give us emission, stimulated emission, because light is in the surrounding. This will give us absorption. More formally, I usually call it stimulated absorption, just to go parallel in the name of stimulated emission. Of course, absorption, you need to give it something to absorb, okay? So very often that is not mentioned. Now, we have a more concrete formula to see, right? Instead of sensing it. Again, you see the denominator. That refers to what I'm saying, okay? Now, that will be important if this is, that hits the resonance. The second term, similar argument. But here the argument, one more important argument is the following. If this term is important, that is to say, if initial, final is there, okay, then this one cannot be important. Okay, meaning you give me an initial final and then you have a h bar omega, okay? Either you have this term being big or this term being big. When one is big, the other cannot be big. That is the observation, okay? Now, formally, at this point, we should take this thing square. And therefore, you expect to see some cross terms in addition to this thing square and this thing square, okay? What we just argued that I wrote down here, when the one term is big, the other term is small, etc., means that we can take a shortcut. All these cross terms cannot be big because you have one big term multiplied into one tiny term, okay? The same thing goes as the other cross term, okay? A big, B small, A small, B big, all right? Therefore, from this point on, I will ignore all these cross terms. Therefore, we take an easier path. We isolate the discussion. When we discuss absorption, we take this term and move forward. We take this term alone and AF square, okay? When we go to discuss emission, we take this and take this thing square. That is the strategy. And that is valid. Therefore, we take the absorption term and start discussing the physics. By that, I mean the following. You take this and do an absolute square. Okay, so I do that. You take this, you pull out half of this. Let me see, what do you do? Okay, so basically you do something like that. EI theta minus 1, okay? So you pull out half of it, and then you have half of it minus half of the angle. Okay, that is the trick. And therefore, you will pick up a sign. Okay, well, divided by 2i, things like that. Okay, so do you follow the trick? And then we will get equation 17. So again, there may be one step or two for you to fill in, all right? After doing the trick, you will see that A2 alone for the second term gives us this form. I still have a half the angle here, okay? After doing that, I have a IH bar included at the beginning. Okay, so this is already there. That help us cancel some of this thing when we do the chain rule. Next step, take this thing and take a square. That will be the probability of finding the atom in the second state at time t. Therefore, we get a very nice answer. This is the answer. Okay, closed form, rather nice. The next thing to do is to analyze this particular function. Okay, that is a very rich function to analyze for several reasons. Now, this function looks rather complicated, but I hope that you know, for example, sine x over x, when x goes to 0 is something, okay, it's 1. Okay, I hope that you know that, okay? So if you know that, then you are on the right track. It is complicated in the following sense. You can see this as a function of different variables. For example, if I call this function f, immediately I can see it as a function of omega. In this case, I have E1, E2 absorption, okay? E2 is higher. And then I'm playing with what if I change my incident light's omega. But it can also be seen as a function of time. That is to say, if I have E1, E2 fixed, and omega also fixed, then I see how does this thing change with time. Well, that's natural because all this omega t are there, okay? Now, even worse, or even good, better, you can even see that as a function of E2 minus E1, okay? You have omega and time, and now you look at, E1 is here. There are many possible final states. I'm trying to see if the final state is slightly farther apart, what is the probability? Slightly closer to E1, what is the probability? So first of all, when we go into the discussion, you find it, oh, very complicated. Good, it should be. It only shows that this formula is powerful, okay? It has everything in it, okay? So now let me take you through step by step. For the moment, we will focus on this part. Just to remind you, we have a spatial integral to do, okay? Of course, if your eyes are sharp, for the two states involved, if this is 0, you don't do anything anymore. You just say disallowed, forbidden, done, okay? However, for the moment, we want to study the feature of this function. Immediately, one thing you want to do may be, you see this argument, and this is slightly different by t over 2h bar, okay? So if you put back t squared over 4h bar squared, you really see this sine x over x square function. Now let me clean the thing up, okay? So now let me focus on this behavior. On this page, my real point is, let's take some fixed time. So I'm not worrying about this as a function of time. I take it as given a number. And therefore, I'm more focused on seeing this as a function of omega. But if you see the formula, sufficient time, you can take this picture and then translate it to other picture when you think about it as a different variable function. Okay, so then let's plot it out. All right. Here I'm plotting this funny thing, this ratio, on the y-axis, and then on the x-axis. Pay attention. I'm seeing it as a function of omega, but more conveniently, I'm plotting it as h bar over E2 minus E1. That is to say, when this thing is 1, it means I'm hitting at the right energy. Okay, so when this thing you see 1, that means I hit this difference. All right, now let's look at the function. Fix the time. You give me a time, so I fixed this here, then I start plotting. I'm plotting it as a function of this ratio. Of course, as expected, if you hit 1, the right thing, this function has a peak, the largest value there. All right. And then you can work out what is this value as well. As I already hinted at, if I multiplied t square over 4h bar square, okay, of course, I shouldn't do that. I have to put it back. How to cancel it? Okay, so that will be okay, right? I'm multiplying to a 1, and then you will see this to be our friend, okay? The limit when it hits the resonance, it will give 1. Thereby, the whole function will have a peak that is t square divided by 4h bar square. So I'm talking about this value, okay? It is this value. Second point, from the peak on both sides, it will drop, okay? And then it will hit at the first minimum, so-called. You see this thing in year 1, in optics, I think, something interference, diffraction pattern, those kind of things. You see the same function. So you hit at the first 0, the minimum here on either side. And if you work out when does it hit 0, so sign will be 0, right? If this goes to pi, right? So you will find that this point is the resonance point 1 plus 2 pi h bar, the energy difference, times t. Basically, it says, for the fixed time t, this range goes like 1 over t. Okay, you see the difference here goes like something over t. Similarly, on the other side, it is 1 minus 2 pi h bar energy difference t. Therefore, this also goes like 1 over t. All right. Now, let me summarize. For this function, we can simply look at the central, this bump, because all the other thing is very small, all right? And this central bump has the following property. The peak takes on value that is t square. I'm not caring about this, okay? Just t square. And the width is like 1 over t, okay? 1 over t on either side, so it's like 1 over t, okay? So all in all, the area under the curve, this bump, is something like t squared times 1 over t. That's to say the bump, the area, is related to time linearly in time. Okay, so okay up to here. Okay. It's okay. Okay, there's a lot of physics here. Okay, some of them I don't want to really go into it, not to confuse you. All these are mathematically step by step true. Actually, this is related to some form of uncertainty relation in energy and time. You only have a finite time, therefore, you will not strictly hit requiring absolutely this denominator must be 0. Okay, you have a small buffer that goes like 1 over t. That you still have some chance to have this stimulated absorption. Okay, now you may think that this is one time, a snapshot. You have a camera, okay? At a time t, boop, you get this. Now you let time goes a little bit farther. You take another picture, okay? It will be of similar form, only that time is now slightly longer. You will see the peak will move up at a later time. The width will become narrower. It will come to here because 1 over t, okay? Do you follow what I'm saying? At a later time, the peak value shoot up, goes like t squared. The width of this central thing get narrower. The width is still 1 over t, but t is longer, the width is smaller. But the area under the curve remains something that goes like t. Okay? And now you see the requirement will be stricter and stricter for the energy criteria. Okay? So this is summarized here. The value here is this t squared. The width here is 1 over t. Okay? The total width is twice that, but it's still 1 over t. Okay? Therefore, when we analyze this function, we have the following observation. This function is sharply peaked at this particular energy at reasonably time. You don't need very long time, but reasonably time, measurement time. You will see, you will have to require this criteria, okay? And that's common sense. You need to tune your light to be right so that you see absorption. That's true, okay? And more interesting observation is that the area under the curve grows linear in time. Okay, the peak value shoot up t squared, the width string 1 over t. Okay, the area is something like t. You can work out the thing in detail, but I hope that I know that last term you see delta function. The Dirac delta function is some normalization of wave function, right? So in your notes you have that. Therefore, I would like to mention here that this formula, I mean this function, is a representation of delta function as well. It can be represented as the area under the curve goes like t, after you work out the prefactor, something like that, and it requires this particular energy criteria. Okay, that is the behavior so-called at long time. Okay? So we have this formula. That will be useful slightly later. Second point, if you are strictly at resonance, that is to say, you have the luxury to have an excellent laser and so on, but even excellent laser has a width, okay, in frequency. If you can really tune it right at this point, all the physics you pick up is this particular peak, you will see that A square grows like T square, okay? But that is not usually observed in experiment, for the reason that you always have a width in your incident light. There is a spread in frequency. When you have a spread of frequency, we need to use this form of the function and to integrate what you have in your incident light. There are spread in frequency, okay? And at that time, you will see that A square will go like T, and therefore, you will get the transition rate. That is to say, you will get A2T divided by T being a number, and that will govern the chance of an absorption as well as the chance of an emission, okay? So, nice formula to start with. Integration in time, a Fundy factor. The Fundy factor, very rich behavior. You can see it in different viewpoints. I show you that fixed T as a function of the incident light. There is a resonance. If you hit that, the peak is very high, okay? The behavior in time is it will get narrower, the peak shoot up, the width shrinks, the area goes like T. And it's a representation as a delta function, okay? That is what I introduced. With this, stimulated emission is nothing anymore, okay? We go back to the formula. We discussed this. We pick this thing up for the discussion now. The steps are almost identical, except this is switched, okay? Therefore, you expect to see more or less the same thing. So let me do that. I take the first term responsible for emission. I do the same thing. I take the square, I hit at this funny thing again. The only difference is now initial, final. Initial is higher than the final. We expect h bar omega equal initial minus final, something big will happen. Therefore, we don't need to repeat the discussion again. We just copy results, okay? It is more interesting to compare side by side the formula. Now, instead of labeling the two states initial and final, let's consider the situation where we simply label the state by 1 and 2. So I have 1 here, 2 here, okay? The more important thing is that this is lower energy, this is higher energy. There are two different scenarios. Maybe initially the atom is here, so that will become my initial. And then through emission, the emission term, this will be my final, okay? And therefore, when this thing goes with E initial minus E final, or E2 minus E1, stimulated emission will work, right? Will happily work. That term will be big. Similarly, there will be occasion that this is the initial state, this is the final state, and then that will be the absorption scenario. Summarizing, if you have two states like this, and the h bar omega coming in, depending on whether your guess of atoms, right? Maybe some of them here, some of them there. You will get both stimulated emission and stimulated absorption. Okay? It is a dynamical process in a gas of atom. All right? So now, for this case, it is educational to repeat the answer and write it as E1, E2 instead of initial EI and final EF. Let's look at absorption. Absorption will require h bar omega equals E2 minus E1. 2 is the higher one, okay? So you will have this factor, all right? For stimulated emission, okay? Again, you will have the same form. If you call this higher, lower, okay, instead of initial, final. All you need is that h bar omega hits the right energy difference. That is the physics, okay? So let me summarize. As far as the time factor is concerned, when the two levels you are talking about are the same two levels, h bar omega comes in, you will have stimulated emission, stimulated absorption at the same time, and the formula are the same. Okay? One additional point. There is a spatial integral. For absorption, okay, 1 is the initial, 2 is the final, therefore you will expect the matrix element is set to 1. For this one, same two state, initial is here, final is here, therefore you will expect to pick up the spatial integral element is set 1, 2. But we are fortunate, okay, and mathematically correct that they are related by the complex conjugate, and we pick up not alone the Z element, but this thing square. So therefore, they are the same, okay? So let me summarize what is important on this page. It says the following, a very important point, okay? Stimulated absorption and stimulated emission between two states occur with the same probability, okay? Of course, they are under the same condition, meaning the same stimulation of light, okay? The same intensity, for example, the same E square, the amplitude of the field, E0 square, okay? That is the intensity, proportional to the intensity. So that is to say, you have two levels, h bar omega is right, then you will have absorption, emission, and they occur with equal probability. If atom is there, the probability going up equals if atom is there, the probability coming down. Okay, now that is highly non-trivial, but we work it out. This is the consequence of our analysis. Okay, and that has some very important consequence actually, and it will come out when we discuss slightly later Einstein's 1917 work on what is now popularly called Einstein's A and B coefficients. Okay, so let's take a break now, and then we will, so we are done with the time integral. We see that two terms give us absorption, emission, nice, okay? Next, we will go back to the spatial integral, this thing, and analyze what are the selection rules. You will see common sense also come out naturally, okay? So let's take a break now. and call your friends to come to class.